Classical mechanics begins with the concepts of the idea of a particle of mass m and charge q located in a three-dimensional space with a right-handed coordinate system x, y, and z. The particle is positioned at the end of a vector r in 3 dimensions, where r is a function of time and consists of 3 components: x of t, y of t, and z of t, 3 functions of one parameter. The velocity is then defined as the derivative of the position with respect to time. The first derivative of the x-coordinate, the y-coordinate, and the z-coordinate make up this vector components, vx, vy, and vz. The momentum is defined as the mass times that velocity, and a scalar times a vector is always defined as the scalar times the first component times the second component and times the third component, giving you 3 new components. The acceleration is then defined as the derivative of the velocity vector with respect to time, which is the first derivative of each of the velocity components, or if you wish, the second derivative with respect to time of the position in the x, the y, and the z direction, these coordinates. By Taylor's theorem, we might expect that we would have to work forever to know all of the different derivatives with respect to time for all powers n. This would certainly give us the function r as a function of time if we knew every single parameter, every single derivative. But Newton's second law stops that process at the second derivative with the statement that the second derivative of the momentum with respect to time is equal to the total force. It is thus our objective to now understand forces. The fundamental philosophy is the following. A complex system is made of many component masses, perhaps with charge, and maybe other quantum numbers. And that complex system can be understood, by understood we mean predicted, by solving the derivative of the momentum of each particle with respect to time as it's equal to the total force on that particle, where the force on any particle is given as the sum over j of the force of the jth particle on the ith over all j particles. I want to emphasize that we just mentioned that to understand implies that we can predict, and to predict implies that we can understand. And to predict means that we know the state of the system at all times from knowing the state at one particular time, say t0. Thus, the central problem of classical mechanics is given the forces of I onto j, then to solve these equations: the first derivative of the momenta as a vector for the ith particle with respect to time equal to the sum over all of the j particles, force of j onto I for all I particles. Now this is a coupled system of vector equations for all of the different particles, where this should be a vector right here. So what is our problem? Our problem is then to understand what the forces are in classical mechanics. There are 4 main forces. The strong force, or sometimes called the nuclear force, and it has a relative strength of approximately 1. The electromagnetic force, which has a strength of approximately 10 to the minus 2, 1/100th of the strong force. The weak force, which is approximately 10 to the minus 14th, and the gravitational force, which is about 10 to the minus 39th. 2 of these, the strong or nuclear force and the weak force, have very short ranges of the order of atomic distances. But the electromagnetic force and the gravitational force have infinite range. This actually is due to the fact that the particle which is exchanged between them is not a massive particle, but has a mass of 0. And therefore, because of this mass 0 particle that is exchanged, they have infinite range. Some of the common forces that we are familiar with is, first of all, the Coulomb, or electric force. The constant K is 9 times 10 to the 9th in MKS units, and the force of particle 1 on particle 2 is the negative of K, the constant K, times the charge of the first particle times the charge of the second, divided by the distance between the two particles squared. Here I have written the magnitude of the distance between particle I and particle J, particle 1 and particle 2. I've written it to the third power, and that third power cancels the magnitude of this vector over here, and this vector gives the correct direction to the force of particle 1, the force of particle 1 on particle 2. By contrast, the gravitational force is always attractive. And g, the gravitational constant, we can see is 6.67 times 10 to the minus 11th. And the force of particle 1 on particle 2 is g times m1 times m2, where these are the two masses. Again, divided by the distance squared, which we have written as the distance cubed in order to cancel the magnitude of the vector r1 minus r2. For two positive masses, this sign gives the correct direction for the force of 1 onto 2 when the force is written this way. And we have a negative sign up here, meaning two like charges actually repel each other. For a system near equilibrium, which is very important, the force is normally proportional to the distance away from equilibrium, where k is a constant of proportionality. We notice here that there's a negative sign, and this negative sign implies that the force is in the opposite direction from the distortion. So if you distort a system to the right, the force is back to the left. If you distort it to the left of equilibrium, the force will be in the negative direction. It'll be back to the right. There are other types of dissipative or frictional forces that are very common. The first of these is a force which is proportional to, with a constant b, the velocity. In a similar way to the last equation, we notice that if the velocity is in the positive direction, this force will be in the negative direction because of the minus sign. Likewise, if the velocity is in the negative direction, then this force will be in the positive direction. This is required because the frictional force will always be in the opposite direction of the velocity. Otherwise, the friction would assist the particle in its motion. Now, there's another type of common friction that is shown that is proportional to the normal force between two particles. Here, the frictional force just of one mass that's sliding over another mass is a constant of proportionality, mu, times the normal force between the two objects. All forces arise from the exchange of particles, and this is an extremely important insight into the nature of forces. In other words, forces are one of the things that physicists understand. We understand every force as arising from a particle being exchanged between two objects. For the electromagnetic force up here, the particle that's always exchanged is called a photon. That is essentially a piece of light, a mass 0 particle of spin 1. The graviton is the particle that is exchanged in the gravitational interaction, and the graviton has a spin of 2 and a mass of 0. We will discuss later in the course the particles that are exchanged for the strong and the weak interactions, which are massive and therefore result in the very short range. Without a doubt, one of the most important problems in elementary physics is that of the harmonic oscillator. It turns out that the harmonic oscillator is also critically important for problems that we consider in quantum theory and in Lie groups and in Lie algebras. Therefore, it is essential that we understand the classical foundation for the harmonic oscillator. I will therefore go through the derivation of the solutions of the harmonic oscillator in some detail. We will use this as the foundation of some of the things that we do when we review various formulations of classical mechanics. The harmonic oscillator is basically set up in the following way. We could imagine a wall here with a spring attached and a mass at some distance over here. The mass is simply supported frictionlessly by the surface. There is some external force that may be exerted on the mass. The spring itself will exert a force on the mass, having the property of restoring the mass to some equilibrium point, a distance x away from 0. We can therefore write Newton's equations as the time derivative of the momentum is equal to the total force on the system, or equivalently, mass times acceleration, because the mass in this particular case does not change, and since this is mass, momentum is mass times velocity, we can bring the mass outside of the derivative and end up with the second derivative of position, is going to be equal to the total force. There are three components of this force. There's the Hooke's law, or spring restoration away from equilibrium force, minus k times x, a frictional force, minus b times dx dt, due to the friction in some type of fluid like the air, or maybe this is underwater, plus some other force which we just lump together and call the external force that is not proportional to position. We then bring these two forces here to the left side of the equation and write this as an equation which is proportional with mass to the second derivative, the constant b to the first derivative, and the constant k to the 0th derivative, as equal to the external force on the right-hand side. I want to contrast this with the electrical problem, where we have an electrical circuit with some type of voltage, which we call voltage external, with a capacitor, a resistor, and an inductor. Everyone who is looking at this material has certainly seen the electrical equation that comes from Kirchhoff's laws, which says that the sum of the voltages around a closed loop must be equal to 0. Since this is a positive voltage and each of the voltage drops across the capacitor, the resistor, and the inductor must resist that voltage, we can say that the voltage external must be equal to, the sum of the other three. This equation explicitly says that the inductance, the voltage drop across the inductor, is the inductance times the second derivative of charge with respect to time, or equivalently, L times di dt, where dq dt is equal to the current, plus the voltage drop across the resistor, which is the resistance times the current, or dq dt. And finally, 1 over the charge times the voltage itself. We note that this is exactly the same equation that we have with the harmonic oscillator. It is a second-order linear differential equation, and if this term, V external or F external, is not equal to 0, it is inhomogeneous. If those terms are 0, it is a second-order linear homogeneous differential equation. The important theorem here to understand is that the solution to the inhomogeneous equation, and we speak here of the general solution, the most general solution to this inhomogeneous equation is the most general solution to the homogeneous part of the equation, plus any solution that we can find to the inhomogeneous equation. Consequently, to find the most general solution of the entire equation, we must first solve the homogeneous part. So we set F external equal to 0. Obviously, if we can solve this mechanical system, we have solved the comparable electrical system. So next, we set the right-hand side of the equation equal to 0 to obtain the homogeneous version of the same equation. We wish to solve, therefore, mass times the second derivative plus b, the friction, times the first derivative plus k times x is equal to 0. It turns out that all equations of this form have a solution that is x equals to some constant yet to be determined times the exponent e to the power alpha, which is a constant, times t, the time. This actual equation solves all linear differential equations of all orders, except in particular cases where we end up with a degenerate solution. In those degenerate cases, we can set the solution equal to a t to some power lambda e to the alpha t, where if we need three more solutions, we would set t is equal to 0, t is equal to t to the power 1, t to the power 2, and t to the power 3, and that would give us 3 extra solutions that we could use in the degenerate case. The reason for this is, you recall from differential equation theory, that if we have a second order linear differential equation, we must have 2 independent solutions. If we have a third order, we must have 3 independent solutions. If we had the fifth order, we must have 5 independent solutions. These different solutions will manifest themselves as combinations of different coefficients like this a, which is out front of this equation. We now want to begin looking at the solution of the homogeneous equation. We will try, as we just suggested, the solution x is equal to a e to the alpha t, and we will plug that into this equation to get the following result. This is straightforward because the second derivative pulls down 2 factors of alpha, the first derivative 1 factor of alpha, and this no factors of alpha at all. Obviously, we can factor out a e to the alpha t from the rest of the terms, and since we have now the product of 2 terms that must be equal to 0, it follows that either one or the other of these 2 terms must be 0. This is our solution, a e to the alpha t, and if it's going to be non-trivial, it's not equal to 0. It follows, therefore, that the first term must be equal to 0. Thus we get x is equal to a e to the alpha t is a solution if and only if alpha, and now we set this equal to 0 and solve the quadratic equation, alpha must be equal to minus b over 2m plus or minus the square root of b squared minus 4a b squared times 4 times m times k over 2m. We can rewrite that in this form by extending the square root down and bring the 2m in as a square in the following form. It may look strange that we have written this as the square root of something squared, but that's because we want to give this a definition that later on will be important. Namely, we define omega naught as the square root of k over m, and that will turn out, as you recall from freshman physics, to be the natural frequency of the oscillator if there's no friction present. The term gamma is defined as b over 2m, and with those 2 definitions we can simplify our expression for alpha as minus gamma plus or minus gamma squared minus omega naught squared. We notice that we have exactly 2 solutions, one for the plus sign, one for the minus sign. This means, therefore, that we have exactly 2 different solutions for our second order differential equation as is required. There are exactly 3 cases to this equation that we need to consider. And this happens any time that we have a solution where we have the square root of a squared minus b squared. First of all, if gamma is greater than omega naught, we end up with one case, gamma is equal to omega naught, another case, and gamma is less than omega naught, a third case. The case is resolved in the following way. If gamma is greater than omega naught, this particular solution is called overdamped. That's because gamma, representing the friction, is much more extensive than the oscillatory part, omega naught. And consequently, the solution, x homogeneous, is equal to a combination of the 2 signs that we just found up here for alpha, a times the plus sign in the solution, plus b times the other sign in the solution. We note here that this solution is of the form of a decaying exponential, e to the minus gamma t, and there are 2 other terms. This one looks like it's decaying, but this one looks like it's increasing. It's important to realize that this term that looks like it's increasing as we go along is actually not when it's added to this term over here. The reason is the following. Gamma squared is lessened by some amount omega naught squared. Therefore, this term is less than gamma squared. Therefore, its square root is less than gamma. Therefore, no matter what this term is, this term is smaller than gamma. Therefore, this term will dominate it, and the whole term will be minus some factor times t. Therefore, this term here can never dominate and cause this solution to increase. This solution here decreases even more rapidly. So our total solution for the overdamped case is a linear combination of two decaying exponentials. In the situation where gamma is equal to omega naught, we have a degeneracy because the two signs of the square root when gamma is equal to omega naught are the same. So we end up with only one solution. It is here that we have to add a second solution which is proportional to the time. So now we see that our solution for the homogeneous case is a decaying exponential plus another decaying exponential. One would want to ask here, is this really decaying? T increases, and this of course decreases. It turns out, for those of you who are familiar with the mathematics of the exponential, that the exponential, when it's decaying, will dominate any polynomial, no matter what the power of t out front. This will always cause it to decrease. Likewise, any decreasing power of t, if this is any polynomial to a negative power, and this is an increasing exponential, the whole term will increase. That is because the exponential contains terms of every possible power. The third case is one where gamma is less than omega naught. In this case, we end up with imaginary solution. So we switch the two factors. And since gamma is less than omega naught, we bring the omega naught to the front and define a term omega 1 as the square root of omega naught squared minus gamma 1 squared, which is going to be a real number. And that real positive number is of course going to be multiplied by I because we remove the square root of minus 1. This actually gives us the linear combination of two terms, a decreasing exponential, and a term that is complex, purely imaginary, that we will now show is oscillating.